Section 2 is about relations. We're going to be particularly interested in something called an equivalence relation, which measures in some sense that elements of a set are the same as each other. But before we get there, I need to tell you what a relation is. So we're starting with 2.0, definition of a relation, and some examples. So in maths, a relation is something that relates together elements from a set, that's something that states there's some relationship. We've met some examples of this already, like less than or equal to, or subset, if the objects are sets, or equals, which we've seen in several contexts already. And it tells us that there's some relationship there between that pair of elements. But formally, the definition of a relation is actually much larger. A relation on a set S is just any subset of the Cartesian product of S with itself. So this is, you'll remember, the set of pairs of elements from S, like A comma B in brackets like this, if A and B are both elements of S. So you get these pairs of elements, and the definition here just says some of them are related. That's a relation. The sum of them is a subset. So people don't usually think about relations like this. I encourage you to think about it like that briefly, I suppose. But we've got other notation for this. So if a pair of elements is in our subset, then we're going to write ARB to highlight the idea that it's a relation between two objects. We're probably not going to talk about subsets very much because, well, we've usually got some special symbol for them, which looks more like this. In between A and B. But just for a moment, let's think about all of the possible relations that there might be on a set. There are many possible relations on a set. So for example, even if your set is small, like I'm going to write out 0, 1, 2 here for a small set, that's got 3 elements, which means that this Cartesian product has 9 elements. And we've been thinking about power sets. We know that the size of the set of subsets of something with 9 elements, that's 2 to the 9 possible relations. Let me demonstrate. So if you have a little table here to lay out all the pairs of elements from S cross S, then a relation is just any subset of those. So I could make this little table to say, is A related to B? And then I could just pick some of these elements and say, well, there we go. Notice that I'm picking elements from S cross S. For my relation, I've picked these 3. So in my relation on the screen at the moment, I can write that 0 is related to 0. I can write that 1 is related to 0. I do not write that 0 is related to 1 because it's not in that subset. And I do not write that 2 is related to anything. Well, I do write down that 1 is related to 2 though. So this is not a very nice relation. There's not a lot going on there. Of course, we're going to be interested in relations that have particular properties that actually capture something interesting about the set, which is not this one, I think. Let's have some proper examples. So we've met some of these already. Less than or equal to, that's a relation. It is a subset of pairs of real numbers. And we had a definition a long time ago, I think, for natural numbers, which defined exactly which pairs we're talking about. But we're just going to write x less than or equal to y if x, y is in that set. And probably we're not going to think about that as a subset at all. There's the divides relation on the natural numbers, which we met. We say that m divides n, and we write m divides n with a line if that pair is in the set. But you might like to briefly think about that as a subset of pairs of natural numbers. And for any set S, well, you can make the power set, and then you've got lots of subsets of S, and then you can think about A being a subset of B for 2 of those subsets. That's a relation. Perhaps confusingly, it's a relation on the power set, which means that these pairs lie in power set Cartesian product power set, or power set squared, I suppose. That's quite a large set in general. So this is lots of possibilities for how you set up a relation on subsets of S. Here's one of them. A could be a subset of B. It gives a relationship between the two things. And I do encourage you to spend a minute thinking about how this is itself a subset of pairs of sets. Right, okay. I've got some trivial examples as well. These are not really interesting in their own right, but it's useful to have some examples like this if you're looking for relationships that do or do not have a particular property. Sorry, relations, not relationships. If you're looking for relationships, I can't help you. Right, so part one, I've got a relationship where I've got a relation where everything is related. Some people draw these with arrows if things are related. So if A is related to B, you might draw an arrow from A to B. And in this case, my first relation, everything is related. So I draw arrows, maybe two-headed arrows, between everything and across the middle. And importantly, everything's related to itself. I say all X and all Y, and I mean it. So there's a relationship. There's a relation where everything is related. In the second case, nothing's related. That was much easier to draw. For all X, there does not exist a Y such that X is related to Y. And part three, I've got this relation where everything's related to itself only, which I've written like this. For all X, X is related to Y if and only if Y is equal to X. So there's another one for you as well. Now, some of these have got particular properties. I think the not related one is my favourite. That's going to come up in some of our examples later on. You might be interested in a kind of trivial version of this. So my set has got 4 elements on the screen. There's a version on the empty set where there's nothing there and nothing's related because there's nothing to be related. Although I suppose that's an example where everything's related. And also everything's related to itself if you have the empty set. There's nothing to talk about, so you can say what you like. It's not listening. And then 2.4, I've got one real world example. If we consider the set of all chess players, then we could write A, R, B, if and only if A has ever beaten B at chess. And I picked this example because it's got almost no good properties. It's not mutually exclusive, so you could have A related to B, and sometimes B is also related to A because chess players might have played each other multiple times with multiple outcomes. There are some pairs which neither relation holds. Chess players might not have beaten each other yet. And there's a mess of other relationships out there. So this is my example, I think, where there's not some nice structure. Coming up, we got 2.1, which will look at some properties that relations might or might not have.